Have you ever wondered why salt dissolves in water, but oil doesn't? This is all about the properties of solutions. A solution is a homogeneous mixture comprising two or more substances. The major component is called the solvent, and the minor component is known as the solute. When salt, our solute, is stirred into water, our solvent, it dissolves, creating a solution. But not everything dissolves in water, right? That's where solubility steps in. Solubility is the ability of a solute to dissolve in a solvent. It's influenced by several factors like temperature, pressure, and the nature of the solute and solvent. So, oil doesn't dissolve in water because it's not soluble in it. Now that we understand the basics of solutions, let's delve deeper into the intriguing world of non-electrolytes and electrolytes. You might have heard the terms non-electrolytes and electrolytes, but what do they really mean? Well, to unravel this mystery, let's dive into the realm of chemistry. Non-electrolytes and electrolytes are two types of substances that we encounter when we talk about solutions. A solution, simply put, is a homogeneous mixture of two or more substances. Non-electrolytes are substances that, when dissolved in water, do not produce ions. They remain as entire molecules and hence do not conduct electricity. Picture substances like sugar or ethanol. When we dissolve these in water, they don't break down into ions, rather they spread out as whole molecules. On the flip side, we have electrolytes. These are the real game changers. When electrolytes dissolve in water, they break apart into ions, positively and negatively charged particles. And these ions are responsible for carrying electrical charge. So, electrolytes are substances that form a solution which can conduct electricity. Think of common table salt. When it dissolves in water, it splits into sodium and chloride ions, making the solution capable of conducting electricity. But wait, it gets more interesting. Not all electrolytes are created equal. We have strong electrolytes like sodium chloride that completely ionize when dissolved. Then there are weak electrolytes like vinegar that only partially ionize, producing fewer ions. So, in a nutshell, the key difference between non-electrolytes and electrolytes is their ability, or lack thereof, to produce ions when dissolved in water. This ion formation is what makes electrolytes able to conduct electricity and non-electrolytes not. Isn't it fascinating how these tiny particles behave in different ways, adding layers of complexity to the world of chemistry? With a clear understanding of non-electrolytes and electrolytes, let's move on to the fascinating properties of solutions. Did you know that the properties of a solution can tell us a lot about its components? Well, they certainly do, and that's what we're going to explore in this segment. Let's start with the physical properties. These include the boiling point, freezing point, and osmotic pressure of a solution. When a solute is added to a solvent, these properties change, and the extent of that change can be a big clue about whether our solute is an electrolyte or a non-electrolyte. Electrolyte solutions, for instance, often exhibit a greater change in these physical properties because they break down into ions in solution, effectively increasing the number of particles. Now, let's talk about chemical properties. These involve reactions that occur when a solute is added to a solvent. For instance, neutralization reactions can occur in solutions containing acids and bases. This is a key signature of electrolyte solutions, as non-electrolytes don't typically engage in such reactions. Further, the conductivity of a solution is another significant property. This is where the distinction between electrolytes and non-electrolytes really shines. Electrolyte solutions conduct electricity because they contain free ions that can move and carry a charge. On the other hand, non-electrolyte solutions don't conduct electricity because they don't produce ions when dissolved. We also have colligative properties, which depend solely on the number of solute particles and not on their identity. This is where things like vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure come into play. These properties are especially useful in determining the molar mass of a solute. There's so much we can learn about a solution just by observing its properties. They give us insight into the nature of the solute and solvent, their interactions, and the overall behavior of the solution. And understanding these properties isn't just an intellectual exercise. It's a fundamental part of many practical applications, from industrial processes to medical treatments. Knowing the properties of solutions is crucial. but it's even more interesting to discuss the types of solutions. So let's keep the curiosity alive and continue our journey into the fascinating world of solutions. Solutions can be more than just a simple mix of solute and solvent. Let's explore the different types. In the realm of chemistry, there are two primary types of solutions we need to discuss: ideal and real solutions. Let's start with ideal solutions. These are the perfect textbook examples of solutions where the intermolecular forces between the solute and solvent are identical. In other words, when the solute dissolves, it simply steps into the shoes of the solvent particles it replaced. This means that the physical properties of the solution, like boiling point and vapor pressure, can be predicted using simple mathematical models. A prime example of an ideal solution is the combination of benzene and toluene, two substances with similar molecular structures and intermolecular forces. Now, let's turn to real solutions. In contrast to their ideal counterparts, real solutions exist when the intermolecular forces between the solute and solvent are different. This can lead to some interesting effects. For instance, the solution might exhibit a lower or higher boiling point than predicted. This is due to the fact that the interactions between molecules in a real solution can be stronger or weaker than in an ideal solution. A common example of a real solution is a mixture of ethanol and water. Here, the hydrogen bonding between the molecules leads to a lower vapor pressure than what would be expected in an ideal solution. So, you might be wondering, why does this matter? Well, by understanding the types of solutions, we can predict how a solution will behave under certain conditions. This is crucial in many industries, from pharmaceuticals to food and beverage production. Understanding the types of solutions sets the stage to discuss Raoult's law and its deviations. So, if you're ready to take your knowledge of solutions to the next level, stay tuned. There's plenty more chemistry to uncover. Raoult's law is a fundamental concept in chemistry, but what happens when it deviates? Raoult's law plays a central role in our understanding of solutions. It's the backbone of solution chemistry, explaining how the vapor pressure of a solvent in a solution changes as we add solute particles. Simply put, Raoult's law states that the vapor pressure of a component in a mixture is equal to the vapor pressure of the pure component multiplied by its mole fraction in the mixture. This law gives us insights into the behavior of ideal solutions, where the interactions between the solute and solvent molecules are identical. Essentially, it's like envisioning a world where all molecules are best friends and get along perfectly. But alas, the real world is not so ideal. That's where deviations from Raoult's law come into play. There are two types of deviations: positive and negative. Positive deviations occur when the interactions between the solute and solvent are weaker than those in the pure components. In this case, the molecules would rather escape to the vapor phase than stick around in the solution. As you might guess, this leads to a higher vapor pressure than Raoult's law predicts. On the flip side, we have negative deviations. These occur when the solute and solvent molecules get along a little too well. They cling to each other more strongly than they would in the pure state, resulting in a lower vapor pressure than expected from Raoult's law. These deviations are not mere exceptions to the rule. They're crucial in helping us understand the behavior of real solutions. They tell us about the interactions between different molecules, guiding us in designing processes like distillation, where we separate components of a mixture based on their different boiling points. So, while the ideal world of Raoult's law might seem simple and straightforward, it's the deviations that truly shine a light on the complex and captivating world of solutions. Grasping Raoult's law and its deviations is key to understanding the boiling point diagram and distillation techniques. Ever wondered how chemists separate mixtures? Let's uncover the secrets of distillation. At the heart of it all is the boiling point diagram, a graphical representation mapping the relationship between pressure, temperature, and the composition of a mixture. It's a roadmap guiding chemists to the precise conditions needed to boil off each component of a mixture separately. Now let's dive into the world of distillation techniques, starting with fractional distillation. This method hinges on the fact that different substances boil at different temperatures. By gradually increasing the heat, chemists can isolate each component in a mixture, one by one. On to steam distillation, a technique used when compounds are heat sensitive. By introducing steam, the boiling point of the mixture is lowered, allowing the heat-sensitive compound to evaporate without decomposing. The journey through the world of solutions, from their properties to distillation techniques, is truly fascinating.